Hello, welcome back. Now it's my great honor and pleasure to introduce Jack Spielberg from the Arizona State University. And I'm very happy about it because today is a special day. Today is the 4th of July. So we celebrate the American independence by a talk by an American speaker. Better still, Jack, in order to honor the location at which he delivers his talk, will say something about the Polish spaces, right? It was in your abstract.
Yeah, well, I'm afraid I won't say it in the talk.
But you use that.
But I can. I thought it was enough to put it in the abstract.
Exactly. Okay, so without any further ado, Jack Spielberg and its sister bundles containing the Effros-Shen algebras. The floor is yours. Take it away.
Thanks, Piotr, and thanks all of the organizers and especially Piotr for inviting me to come into the talk. So I thought I would begin by recalling what the Effros-Shen algebras are. Okay, well, push comes to shove when we don't use that. So let T be an irrational number in the unit interval. And then according to George Eliot's first classification theorem, namely of AF algebras, there's a unique simple unital AF algebra whose K0 group is Z squared. And we think of that in the form of all real numbers of the form Z plus M plus Tn on an n integers. And then the positive cone in K0 should be the positive real numbers of that form. And the class of the identity element should be the number 1. So this is exactly pinning down which AF algebra we're talking about. And then Effros-Shen realized this AF algebra explicitly. And to do this, they used the continued fraction expansion of real numbers. So for this irrational number in the unit interval T, there's a unique, infinite, simple continued fraction expansion for this number. So the classical notation is with these square brackets. The initial 0 there is actually the integer part of our number. Since it's in the open interval, the integer part is 0. I've since found that not everybody writes that initial 0, but I get confused without it because there should be an integer part in fraction expansion. And it looks like this. It's this 1 over A1 plus 1 over A2 plus 1 over ... So like this stuff. So it goes on forever. And it's one of these paradoxical infinite descriptions of something that's really gotten from a limiting expression. Now, the fact that it's a simple continued fraction means that the numbers AI are positive integers. Oh, and this gives me the point of saying that if n plus is the positive integers, then you know that I include 0 in the natural numbers. One of many arbitrary 0-1 choices we make, and the other obvious one will come up in a few minutes. So to understand this infinite continued fraction, we look at the finite initial portions of it. So the nth convergent is the rational number we get by using just the first n terms. And it's usually written Pn over Qn in lowest terms. And the classical theory says that these convergence converge to the number t that then goes to infinity. And the numerator and denominator satisfy these recurrence relations. So the initial values are here. The first fraction is 0 over 1, and the second fraction is 1 over A1, which, as you see, is sort of the first approximation to this number that we get just using the beginning of the data. And then we use the numbers an and the previous terms to describe the later fraction. So Effros-Shen realized that with these recurrence relations, we can give unital embeddings of finite dimensional matrix algebras, finite dimensional C-star algebras. So we look at the direct sum of matrix algebras of size 2 consecutive denominators, so Qn minus 1 and Qn minus 2, and embed it into the next one, Qn and Qn minus 1, using multiplicities given by this matrix. The point, though, is that you look at this recurrence relation, we can fit an copies of the 2n minus 1 matrices and one copy of the Qn-2 matrices inside the Qn matrices. And that's what I'm showing here. If X is of size Qn-1, Y is of size Qn-2, then AN copies of X plus Y exactly fits uniformly into MQn. And then, well, so there was a tremendously steep learning curve for this smart whiteboard at the Impont Institute. Now I'm finding that every electronic device has a steep learning curve. And of course, X in MQn-1 fits exactly into MQn. We get unital embeddings of finite dimensional C-star algebra this way. And that gives us an inductive system. And so they define the C-star algebra A sub T with the closure of that increasing union of finite dimensional C-star algebra. Well, so you have to take this inductive system and realize it is continuous. This is really an abbreviation for the inductive limit. So that's the Effros-Shen algebra. So it's an AF algebra, and it's easy to see that it's, well, their paper, they explain why it's has the right K theory. Sorry, I should. So in fact, Elliott's classification theorem, well, in conjunction with the Effros-Shen theorem, characterizing A0 groups of AF algebras as unperforated ordered abelian groups satisfying Riesz interpolation. And the theorem is that every such group is an inductive limit of simplicial abelian groups, Z to the N with the standard first quadrant positive point. And they, Effros and Shen in their paper, they really produce that structure with the same process really. And then from there they back up to the matrix. Okay, so what do we have from this? For any sequence of positive integers, we produce this irrational number of the unit interval. That's this map. This is well known to be a homeomorphism. And this is the Polish space. Right? So the irrational numbers of the unit interval will be remetrized as a separable complete metric space. And you can realize it as this product space as well. And now we build a bundle of C-star algebras by just using these Effros-Shen algebras about the irrational numbers, projecting down to the irrational numbers in the interval. And this is actually a continuous C-star bundle in the sense that it's the bundle derived from a continuous field of C-star algebras. But of course, the base space is this Polish space that's not locally compact. So what we would really like to do is have a bundle over the interval, which is a locally compact space or a compact space. And then we have something where we can look more, hopefully for a C-star algebra. So what happens at the rational numbers? Well, again, this is a classical theory. The simple continued fraction for a rational number, every rational number has exactly two finite simple continued fractions. So if one of them we write this way, with A1 up to AN, of course, that AN you could write as AN minus 1 plus 1 over 1. So we can extend our finite continued fraction one step if we make this sort of move. And so this is the second way of writing this as a continued fraction. Well, once we have a continued fraction, we have our convergence just as before, except the sequence of convergence ends. And the last convergent is actually the rational number T. So we get two different finite dimensional C-star algebras. I'll just give them these names. Yes, you can't linger on this too long. So the larger of the Q's, of course, that's the denominator of the final result. That's the denominator of the fraction T. But the Qn minus 1 and the Qn prime, the other sum ends will be different. So we really have two different finite dimensional C-star algebras. to put at each rational number. Now, it's an interesting fact about continued fractions. This, if you've read that chapter of Hardy and Wright or someplace about continued fractions, you notice that the even convergence increased towards the number, and the odd convergence decreased towards the number. So because of that, okay, this sounds like the opposite of what I just said, but in fact, what happens is that the even length expansion for a irrational, well, no, what it means is if you take a number, how am I saying this? So this number t, we have these two continued fraction expansions. One of them ends with an even index and the other with an odd index. So the even index form corresponds to approximating the number t from the right. So if you look at numbers a little bit bigger than t, their continued fraction expansion is an extension of the even one. Whereas if you approximate t from the left, you're looking at a continued fraction expansion that extends the other version. So we have these two different ways of approximating t. And so we might call the algebras, here I chose AT plus and AT minus for the two different. And that means that really we should add, so we have the irrational numbers handled already. We should add two new points for each rational number, t plus and t minus. In other words, we should disconnect the interval of the rational numbers to make a kind of Tempe set. Okay, I'm going to ignore the endpoint 0 and 1 from the form. So it's a locally compact Tempe set. And then, oops. And then we can put in now all of these algebras. So we have two algebras for each rational number. And we get a continuous C-star bundle over this locally compact. So it's some solution to our original question, but not quite the one we're hoping for. So to get a bundle over the interval, I'm going to use a different construction. So now I'm not going to dwell on this, but the usual way of presenting AF algebra by means of what is called a Bradley diagram. And this is the Bradley diagram for the AT. So these in parentheses just tells us how many edges between the two vertices. And the numbers at the vertices tell us the size of the matrix algebra. Okay, if you've not learned about Bradley diagrams and AF algebras, it doesn't really matter. Because you can equally well describe these using a directed graph. So we turn the Bradley diagram into a directed graph. And here I've actually written out the A1 different edges from V2, V1, so on. So you can see what this graph looks like. Everything, so now I have to admit that I'm using the Australian convention. So possibly the only person here who's using the Australian convention, but we need a little salt in every dish. So, of course, this graph algebra has infinitely many vertices, so it's a non-unital graph algebra. So we cut it down by the projection of the first vertex. We get something Morita equivalent to the whole thing, and that's the algebra that's AT. So the Effros-Shen algebra is realized as a corner of the graph algebra. And now, right, so let's say something about how you do this graph algebra. Of course, we all know this, right? But I find I don't know anything when I go to talk, so it's good to review things. So this directed graph has no singular vertices, so the boundary is just the infinite paths. So if we have an infinite path whose range is the initial vertex V1, we use the cylinder set notation. So Kevin talked about this yesterday. All infinite paths that begin with that fixed segment mu. And the typical generator of the graph algebra is an element of this form, S mu star. So mu and nu are two of these things that have the same source so that you can actually do this multiplication. And we think of it as a partial homeomorphism between these two cylinders. And that's one way of thinking about how graph algebras are built. And I'm not going to talk about the groupoid, but that's what's underneath the groupoid as well. Okay, so if we look back at this graph, we can see that the numbers Qn and Qn minus 1, Qn is really counting how many paths there are between the vertex at the left end top and say Vn plus 1, which would be up here. And Qn minus 1 counts how many paths there are to the lower side. So the paths of these lengths are really counting or enumerating the matrix, the diagonal matrix unit in our finite dimensional feature algebras. And so the S mu S nu star is really like this typical matrix unit in this nth stage finite dimension. So the important takeaway from this, and this is a kind of intuitive thing from this discussion, is that the action given by these partial homeomorphisms is a free action in the appropriate sense. Just commuting matrix units. Okay, so that's enough about the classical version of the Effros-Shen algebras. Now, I want to replace E with a different kind of structure to address this problem of filling in algebras at the rational numbers. So I want to replace the directed graph with what I call a category of paths. And I've drawn it this way. So instead of choosing an infinite sequence of positive integers, we choose an infinite sequence of non-negative integers. I forgot to say this on my first slide, but from this point onward, this is joint work with Ian Mitchell, who did the initial version of this in his PhD thesis, and afterwards we did the complete version together. So we choose this sequence of non-negative integers, but we insist that infinitely many of them be non-zero. And then we do the same kind of upper portion as in the previous picture, but now K1, K2, K3, those tell us how many edges are between successive vertices. And there could be some pair of vertices with no extra edges put in there, but infinitely often we have to present some edges. And now below, instead of what we had before, I have these dotted and dashed edges, alphas and betas. And if you're familiar with two graphs, you'll recognize this as a two graph. It's a higher rank graph. We make identifications amongst our paths. So a sequence of edges, say alpha 1 and beta 2, to be identified with a path beta 1 alpha 2. And this is the basic idea of a category of paths, is the directed graph, well, you can think of it as like a directed graph with some identification. So it's really not a directed graph. It's actually a left cancellative small category. So in fact, this one has right cancellation as well and no non-trivial inverses. I call that a category of paths. Not so important, but it does make the analysis easier. But just this portion with the alphas and betas is actually a two graph. So if you're familiar at all with higher rank graphs, you'll recognize that there. And I can just say my motivation for trying to study these things is that I find higher rank graphs have a structure that's so rigid, it's extremely difficult to play with. And like allowing almost any kind of identifications instead of rigidly controlled ones, it's easier to come up with examples. Like this. This was sort of the simplest example of a category of paths that wasn't a higher rank graph that we could come up with for study.
Wait, but I'm confused. So what do you mean it is a two graph if it's not a higher rank graph?
Oh no, just the portion of alphas and betas is a two graph.
Ah, okay.
And what we've done is we've glued on these extra
Okay.
edges that have no other relation. So the whole thing is not a K graph.
Okay.
This has this sub two graph.
Okay, okay.
That's very important.
Thank you.
So categories of paths define C-star algebras in the exact same way that you get from directed graphs and other kinds of examples. The easiest way is to go through a groupoid, but I don't want to talk about that. Let's just analyze this example a bit. And first, let's think about the alphas and betas. So because of the commutation relations, a sequence of edges of the form alpha I and beta j can be rearranged in any order. All that matters is how many of the edges are labeled alpha and how many are labeled beta. So a typical element in this category of path lambda looks something like this. So we can start with maybe some alphas and betas, maybe none, maybe some, and then we put in an edge labeled gamma. We could put in several edges labeled gamma, or maybe we could put in some more alphas and betas, and then gamma, alphas, betas, gamma. right? Some finite list of things like this. Now, it's tempting to think of this as an infinite path, but of course this is a family of infinite paths, because this expression alpha I beta j really represents many different paths in our original graph, but they're all identified under the identification key. So what are the quote infinite paths, the boundary? Well, there are two ways to get one. We could just keep repeating this kind of structure. So some alphas and betas, then a gamma, alpha, beta, gamma, on and on forever. Or we could take a finite portion like that and then use only an alphas and betas afterwards. So I write that as a alpha to the p, beta to the q, where p plus either p or q or both are equal to infinity. And these two different kinds of boundary paths are what make the structure interesting. But just like for the corrected graph case, our typical element of a total set looks like S mu star, where mu nu are paths, but they no longer act like matrix units. So in particular, let me single out this element. This element says, take an infinite path. If the first edge is alpha, remove it and replace it by beta. Of course, if the first edge is gamma 1 something, then we don't act on that. But the point is that if we look at this particular infinite path with all alphas and betas, infinitely many of each, if you remove beta, you don't change that. And then if you stick alpha back on, remove alpha, you don't change it. Sticking beta back on doesn't change it. It's a fixed point for this non-trivial partial homeomorphism. So there's isotropy in the groupoid that underlies this category of paths, which is very different from the Effros-Shen case where you really have a principal groupoid.
Sorry, just a very stupid question.
Yeah.
What's the difference between alpha and alpha 1, beta and beta 1?
Oh, so alpha is a generic name. So if I write V1 alpha, you know that's really alpha 1.
Okay, okay, okay.
So V1 alpha squared would mean alpha 1, alpha 2. Just a convenient way to write things down. And I'm going to be sloppy about it.
Okay.
So this is a very different kind of structure from the traditional, the classical way of writing these algebras. Well, why are they these algebras? This is the theorem that Ian and I proved. So we take one of these sequences, Ki, and we form this different kind of continued fraction. So now, since the Ki's can be 0 infinitely often, there's lots of, it's not a simple continued fraction, but it still converges to an irrational number in the unit interval. And every irrational number in the unit interval has a unique expansion of this special form for some sequence Ki like this. And these are actually fairly easy to prove with continued fractions, just fiddling around. It comes up in our arguments. But the important part is this third part, namely the corner of the C-star algebra you get by looking at the first vertex recovers the Effros-Shen. So this was quite a surprise to us that we actually found something interesting with this ad hoc construction. So again, it's very different. We're getting a groupoid with isotropy, so it's not an AF groupoid, even though the C-star algebra of the groupoid is AF. So again, we thought that was unusual, and I think it's the first such example. Okay, very briefly, the proof has 3 steps. First, we have to calculate the Elliott invariant of the C-star algebra. And this was a huge amount of work. Once we had done that, though, we had enough structure to easily show that the algebra is classifiable. So simple unital was easy. Nuclear, UCT class, finite nuclear dimension is maybe the hardest one, but it comes out very easily from the structure. So once we know that it's classifiable, there's this magic theorem of infinitely many people that lets us identify it by means of this Elliott invariant. So we know that it is isomorphic to the Effros-Shen algebra. But of course, it means that it's essentially a non-constructive proof. So we can't exhibit this as an inductive limit of finite dimensional T-collection. We just know that it must be the right thing because of this T-collection. Okay, so what happens at rational numbers in this case? So let's suppose we have a sequence Ki of natural numbers that is only finitely non-zero. For example, let's let M be the last entry of the sequence that's positive. Well, we still actually get a convergent non-simple continued fraction. So this infinite sequence actually becomes this 1 0 1 0 1 0 pattern after the M term. And it turns out that that reduces just to this finite non-simple. So every rational number in the unit interval has a unique expansion of this form. Unlike the standard version where there are two expansions, here we have got a unique expansion. So this way of presenting numbers chooses for us one of the two possible expansions. In fact, it chooses the even one, as it turns out. So now we get a map from the infinite product of natural numbers to the half-open interval, sending an infinite sequence of natural numbers to this uncontinued fraction. And this map pi is actually bijective and continuous, and its inverse map is continuous from the right on the interval, which is puzzling. But I think it's due to the fact that at rational numbers, we're actually picking off the even length version of classical, which is the limit from the right. Of course, the limit from the left goes haywire. You couldn't possibly get a homeomorphism between a non-compact space and a locally compact space. Now, in the case where K is only finitely non-zero, all those extra edges labeled gamma expire after a finite amount of time, and then you have only the alpha and beta edges afterwards. And this means that the boundary of this category of paths is finite. But after the initial finitely many ways of putting in gamma edges, we have only alpha infinity, beta infinity to finish off the maximal. So in this case, we have to use all infinite paths instead of without. So it's somewhere a non-standard kind of choice. Usually you choose either the whole thing or the boundary. Here we're taking something in between, but that's okay. It comes up in a natural way. And we find that the algebra we're getting for this finitely non-zero K is an extension. This turned out to be very interesting, I thought. So it's an extension of matrices over the functions on the circle by direct sum of two copies of something like that. And that gives us a single algebra to offer at rational numbers. And so we actually get a bundle of algebras over the half-open interval by using these algebras at the rational and the Effros-Shen algebra. Okay, so what can we say about this bundle? Okay, now I think this is a little bit interesting. How do you topologize this bundle to get some sort of a bundle of C-star algebras in the technical sense? So to study this question, we have to look at a typical element that generates the C-star algebra. That's one of these S mu stars. So let's pick a mu and a nu of the same length. So for each I, mu I and nu I are either alpha I, beta I, or gamma I to some upper exponent of which gamma edge we're choosing. What we're not doing is saying what's the limit on this, how many gammas we've had. This is a generic element that might belong to one of our algebras. So once we've chosen those, we ask for which K does the element S nu star belong to the corresponding algebra. That would be the algebra at pi of K. Right? Pi takes the sequence of natural numbers down to a real number. And the answer is, of course, is those K for which mu and nu belong to that algebra. So we'll try to write stuff down this way. So we define a sequence Li. So Li is the maximum upper index on an edge gamma I that actually occurs in U. And then we can use those to define our sequence L. So S nu star belongs to a pi of k if and only if the ki's are big enough so that those elements belong to lambda of k. And what this means is that if we look at all the k's for which that happens, so where ki is greater than equal to li, and we push down to the interval, we get a certain subset of the half-open interval. That's the set of t's for which we're getting a non-zero element of our algebra. So we need to know what that set is. So I called that D of L. So let's let M be the largest index of an L that's positive. So in fact, we write L as this sequence like this. So L sub M is non-zero, and after that we have only zero. And now I'm gonna tread on your patience, because I think I find the next part interesting. So if you don't, just close your eyes. So it has to do with this very natural, but maybe not so common decomposition of the half-open interval as a countable disjoint union of half-open intervals. 0 to a half, half to thirds, and so on. So we write it this way: h over h plus 1 to h plus 1 over h plus 2. And now this expression h over h plus 1, we can rewrite this way and see that it's actually just a little bit of continued factor. 0, 1. So we're writing the half-open interval as a countable disjoint union of half-open intervals whose endpoints are bits of continued fraction at this point. So if we look at all the numbers where K1 is greater than or equal to L1, that's again the disjoint union. Now we're only using H greater than or equal to L1. But of course, these intervals match head to tail, so we can combine them together to get this symbol. It's no longer starting at 0, it starts at this other place. Okay, that's the first step, where we have only K1 and L1. Let's look at the second step. So we take one of our intervals, h over h plus 1 to h plus 1 over h plus 2, and we decompose it in the same way, right? So we might say we replace h by h plus some variable increasing from 0 to 1 in order to get points of this interval. And so we'll rewrite those as the disjoint union over L, where the thing we add is this L over L plus 1, or L plus 1 over L plus 2. We're just moving everything into this, taking a little half-open interval and writing it as a disjoint union of half-open interval. So, okay, so let's analyze this thing. So let's look at this general expression, H plus. I'm being very pedantic because this is all very new to me and surprising. So H plus X over H plus 1 plus X, that's what we're looking at. Well, let's just think of it as H plus X over something plus 1. We can divide by that thing and get something that looks like a bit of continued fraction. And if we apply that where X is L over L plus 1, we're now getting 2 bits of continued fraction. I'm always curious to know if this is old hat to somebody, because it was a wonderful discovery for me. So we can write this half-open interval defined by H as a countable disjoint union of half-open intervals, where now we're just extending our continued fraction a little bit longer than before. So again, if we fix K1 at H and look at K2 greater than or equal to L2, we're getting something similar to what we had before, and these match head to tail, so we get a single interval of this form. Right, so it's one of these 2 bits of continued fraction on the left and 1 bit of continued fraction, right? It's 1 step further than what we had before. So here's our stage 2 answer. If we look at 2 steps of our process, K1 greater than or equal to L1, K2 greater than or equal to L2, that's a countable disjoint union of half-open intervals where the left endpoint is a 2-step continued fraction and the right interval. Now, there's a famous book by a famous Polish mathematician, George Gamow, and the book title in English is 1 to Infinity, which I think of as one too many, because infinity is really many. So we'll go right from stage 2 to the general case. So now if we have our original setup was where we had these L1 up to Lm, where Lm was non-zero, and then zeros afterwards. So our set D of L, the points in the interval where S nu star actually belongs to our algebra. So we have M of these inequalities, and we get a countable disjoint union with M-1 parameters, Ki. And now the left endpoint has M step union fraction, and the right endpoint is M-1. So it's just a generalization. Okay, well, oops. At least we see that these funny continued fraction expansions that we were forced to use because of the structure of the situation are actually very natural. So this is supposed to convince you that this way of decomposing the half-open interval is reasonable and justifies the use of these funny continued fractions with one in every other spot. Now let's recall our bundle. So when T is an irrational number, we have the Effros-Shen algebra A2. So we're thinking of it in this strange form that Ian and I found using this category of paths. And at the rational numbers, we have the corresponding thing for a finitely non-zero sequence Ki. So we want to define a continuous field. We can. So we'll use a space of sections to define a continuous field, and then that'll give us a topology on the bundle. So we take one of our elements, S mu star. L is the sequence of Ki, Li's that comes from that sequence where we talked about it before. And now we define a section F. So if T is a real number, we write it in the form pi of K. K is one of our sequences. And the value of F at that point should be exactly our generating element, S mu star, as long as it's an element of our algebra, namely, as long as pi of K is in D of L, or in other words, Ki greater than Li of L, and zero otherwise. So it's sort of a kind of characteristic function of this strange countable union of half-open intervals times this particular element. And this is very natural, right? Because this is exactly putting in this element wherever it's possible and not putting anything when you can't use that. So D of L is exactly the set where this function is non-zero. Now, let's just go back. Right, this set where F is non-zero is this countable union of half-open intervals. So you might say, okay, F is discontinuous at the endpoints of these intervals. It turns out that at the left endpoint, where we have the closed part of the interval, that's exactly where we have some sort of reasonable approximation from the right. So we aren't going to worry about that one. We'll worry only about the right endpoint. And so to manage that, we multiply F by a function in C0 of DL, so something that dies off at that type. Now, these half-open intervals actually don't accumulate at any of the left endpoints. So in fact, that even though it's an infinite union of half-open intervals, it's still a locally compact subset of the reals. So C0 of that set is a reasonable thing. It's really functions that are dying off over the union of these intervals, and on each interval dying off at the right endpoint. We go this way. So we multiply our function F by such a continuous function and use those as sections to define field of P. So it turns out, this is a theorem, we've written out the details, but we haven't made a proof of it yet. But that span defines an upper semi-continuous field of T algebras over the half limit. We aren't quite getting a continuous field, but as I've been told, upper semi-continuous fields are almost just as good. In fact, for many purposes, that's what you expect to find in nature. So this theorem is some sort of a success that we've actually managed to fill in between the Effros-Shen algebras in a reasonable way. Still some time. But there's another way to fill in the bundle at the rational point. So what I said before is that we don't worry about the discontinuity of F at the left endpoint. We just want to remove it at the right endpoint. But we could remove it at both endpoints. So we can look at the interior of D of L. I call that D0 of L. And that just means the union of the open intervals defined by the same endpoint. So let's multiply by functions in C0 of that union of open intervals instead. So we're killing off the function at the left endpoint as well as the right. And now these sections really look like they're continuous. Well, I should say that I'm not an expert in bundles of C-star algebras, but I'm learning and I'm trying to put things together. But continuity of sections is defined in terms of the bundle overall. So you have to look at the norm of a section at each T, and that's a different norm because you're in a different C-star algebra. And it's that norm that has to vary continuously or upper semi-continuously. So it's a little bit complicated. When I call this a continuous section, I'm really not speaking the truth. You have to look a little bit larger to verify this. But in fact, we use these sections to define a bundle, and we really do get a continuous field. But we're losing something, right? So we're losing what happened at the left endpoint. So if we let S be the left endpoint, that's pi of L, then this generator is no longer the value at S of one of our sections. So we can describe this in the following way. Let's let B sub S be those elements of A sub S that actually are values of a section field. Then we can identify this with A at S tilde, where we get S tilde by backing off 1 in the final term of our continuous factor. So we replace LM by LM minus 1, get a slightly simpler rational number from this point of view. And that's the rational number whose algebra we're picking up at that first test. So we're sort of changing the algebra we put at rational numbers, getting something a little bit lower in our hierarchy. So we get a proper subalgebra of A sub S, so we've lost some of the elements. But if we fill in with the Effros-Shen algebras at the irrational numbers, then we get a new bundle. And the theorem is that this one's actually a continuous bundle, not just so sacrifice something to actually get continuity.
By shrinking it a bit.
Yeah, we shrink the algebra at the rational numbers a little bit. I guess that seems reasonable, right? If it's only upper semi-continuous, you have to remove the things that make it distant, not continuous. And in fact, it's sort of nice that it's such a simple fix to fill that.
So that's something that you didn't mention in Warsaw.
Correct. I didn't get this far in my talk. My scribbled notes contain something about it. But luckily, there was something left to talk about here. It's amazing how things can actually work out sometimes. Now, once we had done this, we realized that the same trick will work with the classical Effros-Shen algebra. So back to the very beginning, where we're really using the inductive limit of finite dimensional C-star algebras. So let's recall these two different simple continued fraction expansions for a rational number. The corresponding algebras AT plus and AT minus are these. So let's do the same thing. Let's take the A1 up to AN, that expansion, and back off the last entry. Replace AN by AN minus 1. And then we get a finite dimensional C-star algebra, which I'll call C sub T, corresponding to that expansion of this number T tilde. So it turns out that that's a common subalgebra of both of these. It's sort of leaving off the last little bit. The last little bit of both of them, somehow it's the same, right? There's one here, we're removing one here, and we're back to this thing. So we use this subalgebra at the rational numbers, and again, the Effros-Shen algebras at irrationals, and we get a new bundle, which is now putting a certain finite dimensional C-star algebra at each rational. And we use, well, so now this graph algebra construction, I was trying to make the graph algebra picture of the Effros-Shen look very much like the categories of paths. And they are the same in that they're both generated by these words, S mu star. So we can really use the same kind of argument in the graph algebra picture. And we can prove that C really is continuous C-star bundle as well. So I guess the summary would be that for the classical picture, we use the actual algebras at rational numbers, the ones that we should be using. We have to put in 2 and disconnect the interval, and we get a continuous C-star bundle over a locally compact Cantor set. If we want to get a continuous bundle over the interval, we have to shrink the algebra at the rational. We go to the categories of paths, then we get an upper semi-continuous bundle over the interval. But if we shrink the algebra at the rationals, we can make it a continuous. Okay, well, I only have one more thing to say. So what does this mean? I just don't know. I think the next step is to actually try to describe in some way the C-star algebras of these bundles. But that's, work in progress, and we're trying to figure it out. And that's all I prepared, so I'll stop there.
Okay, so let's fire my questions. Anyone from Zoom?
If you think about this bifurcation at rational points, so you are, in a sense, you are shrinking it or truncating it to obtain some continuous C-star bundle. But what if we could introduce some more generalized version of such a family when such bifurcations are allowed? Because in mathematics, this is a frequent phenomenon of bifurcation. And many systems should be regarded as complete together with these bifurcations. And such truncations are regarded to be unnatural. So this bifurcation must mean something. Is this meaningful in this case, or your goal was from the beginning to obtain a continuous field of C-star algebras?
Yeah, so that's a really profound question that I don't know how to answer. So for the classical example, how do you handle a bifurcation like this? Well, in the classical case, the simplest thing to do is what we proposed, is just break the interval to make a Cantor set. And that's actually a very reasonable thing to do, and happens in many other places in mathematics. When we have this kind of problem at a countable set, you can make a Cantor set instead of your original set and work there. I think what we thought was remarkable was that with this alternative picture of these algebras, we actually get a single algebra with no bifurcation. And the fact that we get an upper semi-continuous bundle there, okay, it's not a continuous bundle, but upper semi-continuous bundles are important in the C-star algebra theory. So I think that's some sort of a victory. And why it is that this truncation repair? Well, it seems reasonable that such a truncation might repair continuity. What does that continuous field say about our situation? So these are the questions to continue studying, but I'm not sure. Do you have some other sense of what might be a bifurcation besides doing this? I mean, my imagination is failing me.
Okay.
Well, I think so. In this case, I think for me, I think it's a quite interesting construction is behind this is this continuous fraction which allows you to take this inductive limit, right? So I think this sort of a number theory aspect. I think this is I was just curious, like this in order to get a C-star algebra or continuous field of this bundle. So what's the corresponding like this nice number theory phenomenon behind? For example, like now the continuous fraction is a two-step recurrence relation, right? Are we allowed to have like a more complicated recurrence relation or something like that?
Let's see. So
yes,
if you look at this alternative
yeah,
kind of continued fraction with the alternating ones,
yeah.
Do we have any sense of what the approximates are in that case that we have to work out? Well, so you can take a finite continued fraction of this funny form and reduce it to a simple continued fraction, continued fraction in a very sort of reasonable way. It still turns out to be of even length. That's sort of important. So I think that's an important sign. But how do you describe the numerator and denominator?
Yes.
I never thought of trying to look that out.
Yeah. I mean,
that's a really good question.
I think there are three pictures here. One side is this recurrence relations. The other side is the graph picture, like this general, the path, this graph combinatorial picture. And the last piece is the C-star algebra. So I think it's quite fascinating how these three elements like they merge together. I mean, this or like one part will get some interesting properties to the others. That's
yeah. So I don't really know much about how properties of the continued fraction will be reflected in the C-star algebra.
Yes,
So
and
so there's a little bit. So one question we addressed was so if you look at the category of paths picture,
yes,
again, we're looking at the cut down by the first vertex. Right? So if you look at the whole thing, so now we have something Morita equivalent to algebra. And so we asked the question, is that actually stable? Is it symmetrical? So it's a question of computing the scale of the positive cone you get from the whole algebra. And that's related to how sparsely, in some sense, how sparsely the non-zero elements of our sequence are and how rapidly they increase. So there's something interesting going along in those lines. And we gave some coarse estimates to show that, you might get a stable algebra and you might not, depending on how you close those things. So that's something that, quickly it became really complicated analysis of different sums and products. We gave sort of a first course estimate to show that we get two different kinds of behavior, but I don't know anything about, even if it's interesting to investigate this or what.
Thank you.
Yeah, so I have two questions. One is very elementary. What is a locally compact Cantor set?
For example, if you take an interval, you can if you remove the middle thirds thing, you get the Cantor set of the interval.
Yeah.
If you do that in every interval bound by integers, you turn the real line into it. But within the real line, you found a subset that's locally compact but totally disconnected and
Okay.
so I would call that a locally compact.
Yeah, sure.
So-
And so no, the other question is about some kind of geometrical meaning, because you have so your parameter space is this locally compact Cantor set. Then whatever happens at rational points. And at irrational points, if you take a fiber at a rational point, that is that sister algebra is also some kind of a non-commutative quotient of a Cantor space, of a compact Cantor space by an equivalence relation, because that is the groupoid of an AF algebra, right? So you have horizontally and vertically some kind of Cantor space. Maybe the global picture is some kind of two-dimensional fractal, and
Sierpinski cascade.
yeah, non-commutative quotient, and you get the total space of this sister bundle. I don't know, it's just some random guess. I don't know.
Yeah,
if
no. I think you're spot on.
Very good guess.
In fact, I think that so you know that so two real numbers give you Morita equivalent Effros-Shen algebras, precisely if they're related by CGL2V.
It's kind of like with quantum torus, right?
Yeah. Of course, the rationals are all equivalent. You can try that with those left field. So we think we've almost written out a careful proof of this. So the Morita equivalences, of course, those are given by equivalence bimodules, but those are really functions on some underlying equivalence of groupoids. And those equivalences of groupoids are really sort of portions of these categories of paths where you connect one to another. So this whole structure, I guess we're hoping we actually build a Fell bundle over the action of this group on the interval that really reduces down to the level of these combinatorial objects and subsets of those. And I think that's the kind of thing you're thinking of. And I don't know where to put some geometry into this picture. So at the countable level, maybe not, but it's fibered over this interval. So there should be something. So when we get closer to writing it down precisely, then maybe we can move the question.
Okay, thanks.
Yes, I would like to continue this.
Continued fraction.
Yes, it's like a continuous fraction. So definitely there is some dynamical aspect of all this construction, which is lost after this truncation to obtain this continuous sister bundle. All these phenomena like this bifurcation, all this iterative process of based on continuous fractions. So my feeling is that there is some more dynamical picture than this static one about the continuous field of sister algebras. The full that this truncation is a trial to forget about some essential part of this dynamical part of this. So the relationship between this groupoid picture and this iterative process. So everything is of dynamical nature.
Yeah.
Together with these bifurcations. So I think that truncating them is a loss of some important dynamical information.
Interesting question. So, on the one hand, I have this sense that, well, we've really truncated very little. So we're saving quite a bit of this structure, even if we drop this last index by 1. So I'm not sure that it's quite as drastically ruined, but maybe it is, I don't know. But my other comment is, it's such a good point you're making about the dynamics. That the first talk I gave about this was at a conference in May in the US, and my title was Still Life with C-star Bundle. Because exactly, I think you've articulated what I have this vague sense about, is that I'm looking at sort of a static picture of something that should be sort of moving in some other way. Wow.
Anybody else? Well, if not, let me ask you something. Could you please go back to the slide where you have a short exact sequence with Effros-Shen algebra?
Oh, this one.
Yes, yes. So if I understood you correctly, the Effros-Shen sister algebra is not a graph sister algebra.
So the Effros-Shen algebra, I mean, at an irrational number.
Irrational, of course.
Yes.
Yes.
No, it is. Well, it's a corner of a graph algebra.
It's a corner.
Yeah. Corner of a
But not a graph.
Not the corner. Now, at a rational number, these algebras we're getting are these extensions.
Mhm.
And I think we talked about this before. So I don't think these are graph algebras either.
Mhm.
Oh no, I think these are not graph algebras, but
Yeah.
I don't know how to prove such a thing.
And the reason why I mention it, because it's important to bear in mind that even though we are extending a graph sister algebra by a graph sister algebra, what you get as an extension is not a graph sister algebra. So graph sister algebras
Not to, yeah.
are not in general closed under extensions. And this it reminds me of an issue we worked on some ages ago with Wojtek Szymański and Rainer Mattes. Because the same situation happens for pullbacks. I mean, you know, you can relate pullbacks of sister algebras to short exact sequences. I mean, Hickson and Roebuck in the standard way. And a very simple pullback of graph sister algebras giving a graph sister algebra is the Podlesh generic quantum sphere. You glue two Teplitz algebras over the symbol maps over the circle. And here you go. Lo and behold, you have a Podlesh quantum sphere. But at a certain moment, we discovered that it's more natural to change one of these morphisms, and one of these maps was the symbol map modified, and then we have again we have a pullback of graph sister algebras of a graph sister algebra, but the result is a mirror quantum sphere. So if you want, this is Heathort CP1, and Wojtek proved that not only it's not isomorphic to Podlesh quantum sphere, it's not even Morita equivalent. And so one of the things which fascinate me, I would like to know what are the properties of morphisms between graph sister algebras, for instance, to guarantee that the pullback sister algebra will be again graph sister algebra.
Well, so if you allow yourself to generalize beyond directed graph, the categories of paths, then it is.
Yeah. Oh, so you have, so that will be closed under pullbacks, right?
Oh, no, I have no idea. But in this example,
Okay.
you know, even if
Okay.
you don't get a graph algebra, it is some sort of
Okay.
light generalization.
Okay.
But they are closed under extensions, right?
These algebras,
Higher rank graph sister algebras.
No.
they're closed under tensor
Under
Tensor
tensor
products,
product.
not extensions.
extensions. That seems really questionable. I don't know.
So let me have a look at Zoom. No. So hello, Kevin. So if there are no more questions, let us thank our speaker again. And God bless America.
We do that.
Stop recording.